Okay, now see certain example based on Coulomb forces. So example number 1. Let 3 charges kept at the corner of an equilateral triangle. Let 3 identical charges kept at the corner of an equilateral triangle, of edge L. So find the force on any one of the charged particle. Find the force on any one of charged particle. This is very basic and fundamental problem, very simple as well as fundamental how we are using here principle of superposition that we want to see here. So according to question here, 3 charges kept at the corner of an equilateral triangle. So let this is your equilateral triangle and charges kept at a corner and each edge having side L. Now we want to force on any of the charge. We can take any of the charge. Suppose we want to calculate the force on this. So as per the principle of superposition, the force on any charge is equal to the vector addition of the force applied by all the charges. Okay. So force on this charge due to this charge in this direction, because both are positive, so repulsion force. So let we are denoting the charges as 1, 2, 3. So we can say force on 1 due to 2, the force 1, 2. Similarly, force on 1 due to charge number 3, and this is also positive. So this direction will be like this. And since these are the 2 forces acting on a charge 1. Now, as per the principle of superposition, resultant force on a charge is equal to the sum of the or vector sum of the forces applied by all the charges. So what can be done here? Now, since all are the identical charges and those are placed at the same distance, so the magnitude of the 2 forces are same. Here magnitude of the forces are same, but their directions are different. So when direction are different, so we cannot directly add, we have to resolve. So we can resolve like this. We can resolve in 2 component, horizontal and vertical. And this angle here 30 degree. So this angle here 60 degree. Similarly, this angle is also here 60 degree because this is your equilateral triangle. And equilateral triangle means angle here 60 degree. So now since the magnitude of the forces are equal, so when we are resolving in horizontal direction, F12 cos 60 and F13 cos 60, these are in the opposite direction, so these forces will cancel. Only the component which are in the vertical direction, that component will remain. So net force will be in this direction. So net force can be given as F12 sin 60 and F13 sin 60, F12 sin 60 plus F13 sin 60, and since magnitude of these 2 forces are equal, so 2 times F12 sin 60 we can write, and now substitute the value. So 2 times F12 1 by 4 pi epsilon naught q square by L square, and sin 60 means here root 3 by 2. So in this manner we can calculate the resultant force on charge q is acting vertically upward and the magnitude of that force is given by this relation. So 2 and 2 you can cancel, so it become your root 3 times q square. It become your root 3 times q square by 4 pi epsilon naught L square. This is the net force on charge q. This is the simplest example, very, very simple example. Now see the another example. Okay, now see the example number 2. So here one point charge q and another a conductor of length L having a charge per unit length lambda. Are kept at distance d c. So according to the question here, so a point charge q and a conductor of length L having linear charge density lambda, kept at a distance d, as shown in diagram. Now find the force of interaction between point charge and charge conductor. Find the force of interaction between point charge and charge conductor. Now, how to solve such type of problem? Here, as we know, Coulomb's law is valid only for point charges, but here one is the charge is point charge, but another charge is not a point charge. Then this come in our mind how we can apply the Coulomb's law. So actually we are applying Coulomb's law for a point charge. Simultaneously we are using principle of superposition. So what we are doing, although this is not a point charge, but any of the object can be said it is the combination or it is the collection of points or particles. Same thing here also. This rod can be taken as a collection of point charges, and different charges are kept at a different distance from this charge q. So we are calculating the force on all those such point charges, then vector addition of all that. So this is nothing, it is also known as the method of integration. But first, before using the method of integration, we will see what are the direction of forces. If direction of forces, all those quantity can be added together algebraically, which are in the same direction, and if the directions are different, then we will follow the vector addition here. So how we can say, this is a point charge, and this is a point charge, and this is your conductor. Now this conductor can be divided into different point charge just like a particle. So if we are taking one particle somewhere here, so the distance of that particle and here is different, and if we are taking another particle here, and this and different distance, so distance are different, but what is the same? Force, direction of force will be same. As this is positive charge and this is also positive charge, direction is same, so directly we can add the algebraic addition with this direction. Okay, so what we are doing here, we can take a small element. That small element is too small. It is just like a point charge at distance r, and the thickness of this element your dr. So this is one of the charge and this is another of the charge, and the charge value on this is let dq, and dq charge in the length dr. Total charge per unit length is lambda. In unit length having charge lambda, so in dr length the charge will be your lambda into dr. Okay, now force between these two. This is the force dF we can say, because we are calculating force for a small part. So a small part means dF, 1 by 4 pi epsilon naught q into dq, and dq is nothing lambda dr by distance between these two your r square. So this is the force between this point charge and this small element. Now same force if we are considering another element, third, fourth, like this. So it means summation of all this. Summation means nothing, it is the integration. So integrate. Now integrate means what could be the limit? Limit means from where to where our this element is changing. Our element can be from this end to this end of the rod. So when our element is at this end, so r value will be your d, and when our element is in this range or this end, then the r value will be your d plus l. So that is called limit. So limit will be your d to d plus l. So f is your 1 by 4 pi epsilon naught q into lambda dr by r square means 1 by r. So this is your 1 by d minus 1 by d plus l. So finally we can write 1 by 4 pi epsilon naught q lambda l by d into d plus l. This is the force between a rod having linear charge density lambda and separation between the rod and the particle is d. So here integration means unknowingly we are using actually principle of superposition. So since direction of force are same, so directly we can integrate. Now see another example. A point charge having charge q and kept at the center of a uniformly charged ring, of radius r having linear charge density lambda, Find the tension on ring. Find the tension on ring. So question is here, a point charge having charge capital Q kept at the center of a uniformly charged ring of radius r. It means this is your uniformly charged ring, and linear charge density is lambda, means charge per unit length is lambda. Okay, lambda is a linear charge density, and the radius of this ring is your capital R, and another charge, a point charge having charge Q, that kept at the center of ring Q charge. Okay, kept at the center of a uniformly charged ring of radius R having linear charge density lambda. Find the tension on ring. So first of all, meaning of the question here, how to get an idea of what is happening here. What is happening here? See, a positive charge Q kept at the center and a positive charge is distributed throughout the circumference of a ring. So what will happen? Due to both are the positive charge, force of repulsion will be there. Due to the force of repulsion, ring will, on every part of the ring, force will act in the radial direction. So from every part of the ring, force will act in the radial direction. The ring will try to extend. When the ring will try to expand, so what will happen? A tension develop on the ring. So that tension we have to calculate actually. Okay, see. So what we will do? We would like to calculate the first forces. Take a small part of the ring and calculate the force on that ring. So how that forces are producing tension, that we are going to calculate here. See. So what I did here, I took a very small segment on that ring, that this part of the segment is making angle theta, this is also making an angle theta. So when we are talking about this part of the segment, this theta normally always remember, whenever we are taking here theta is tending to 0 degree, very, very small. When theta tending to 0, so this becomes just like a point charge. So when point charge here, so how much charge on this part of the ring? Let that charge your dq, and this dq is nothing, lambda charge per unit length, and length of this part, this is radius r, r theta, so 2r theta. 2r theta, this is the charge dq, and this is positive charge, this is positive charge. The force on this part is your in this direction. That force is how much? Same Coulomb formula, 1 by 4 pi epsilon naught q into dq by distance of this charge from the center, r square. And now substitute the value of dq. dq is your lambda into 2r theta, lambda 2r theta by r square. This is the force between charge capital Q and this small element. Due to that force, it will stretch. Ring will stretch like this. So tension develop in the tangential direction like this. When this tension develop here, so tension have two components. If this angle theta, so this angle also theta. So T cos theta and T cos theta of the component of tension in the direction, that will cancel out. So downward force will be here 2T sin theta. This downward force is balancing this one. So at equilibrium we can write 2T sin theta is equal to that force F. Now, as theta is very, very small, so for theta tending to 0, so we can write sin theta is almost equal to theta. So from here, the 2T into theta, that is your F. F value your 1 by 4 pi epsilon naught q lambda 2r theta by r square. Now simplify, we want tension. So 2 theta and 2 theta here cancel, and 1 r and 1 r cancel. So tension will be here 1 by 4 pi epsilon naught q lambda by r. Okay. So likewise we can calculate the tension. Now come to the another problem. This is your third example, I think. Now come to the next problem. 2 point charges having charge plus q, having charge plus q are fixed at a distance d. A point charge kept at the middle of two charges, kept at the middle of two charges. So analyze the equilibrium of that charge. Analyze the equilibrium of that point charge. Equilibrium of that point charge. Okay, see. Meaning of this question is that these are the 2 point charges having charge plus q and plus q, and these two charges are kept at a distance d. Kept at a distance d. Now, a point charge kept at the middle of two charges, a point charge. Middle of the two charges means somewhere here. So this charge may be your plus q or it can be a minus q, that is not given. We can consider both the situation because we are going to analyze the things, what is happening here. Okay, see. So we have to analyze the equilibrium of that point charge. So first of all, equilibrium. Equilibrium means the resultant force is 0. Equilibrium means resultant force is 0 means here, if we are putting here, let's suppose positive charge q at the middle. At the middle means that distance is d by 2. This is also d by 2. So if this is your positive charge, so between this plus q charge and this plus q charge, force of repulsion in this direction, and this plus q and this force of repulsion in this direction. The net force on this charge is 0, no problem. Similarly, if your minus q charge, then the force of attraction in this direction, and this charge is applying force of attraction in this direction. Since this is placed symmetrically between these two charges, so magnitude of forces will be same. Then also resultant force will be 0. Then also there is no problem. It means either we are putting a plus q charge or minus q charge. In both the cases, both charges will be in equilibrium. Now, although both the charges are in equilibrium, but we are having the mainly three type of equilibrium. One is called stable equilibrium, another your unstable equilibrium, third is neutral equilibrium. So we would like to see here if the charges are in equilibrium, so those are in which type of equilibrium. That charge is in which type of equilibrium, stable, unstable or neutral equilibrium. So first, what is the meaning of stable, unstable and neutral equilibrium? Stable equilibrium means the position where the point charge or where a body is in equilibrium is net force is 0. If we are displacing that body from that position, and at displaced position, if we are observing the forces acting on the body opposite to direction of displacement, it means that force will try to bring back the body in equilibrium position. Such type of equilibrium is called your stable equilibrium. It means in stable equilibrium, the force on a particle at displaced position is in opposite to the direction of displacement. And in unstable equilibrium, the force on a charged particle at displaced position is in the direction of displacement. That is your unstable equilibrium. And neutral equilibrium, it means there is no effect on the force, either the body has been displaced slightly or moreover. That is the neutral equilibrium. So what is the main, what we will do here? We will check the forces on a body at displaced position from the equilibrium. Either those forces are opposite to direction of displacement or in the direction of displacement or no effect. If opposite to direction of displacement, then that will be your stable equilibrium, and if in the direction of displacement, unstable equilibrium, no effect in the displacement, the neutral equilibrium. See how we will do. We will consider both the charges, positive and negative, one by one. See, first suppose we are considering positive charge. This is the equilibrium stage. So this line we can say as a equilibrium line, line of equilibrium, or mean position also it can be said. Line of equilibrium. Now if this charge is displaced by let x, it is here, and x is very small. So now distance of this charge from this charge will be your d by 2 minus x, and from this d by 2 plus x. See, first of all, just analysis. Just we are doing analysis. What I observe, if the positive charge displaced in that direction by x, so distance between plus q and this q here decreases. So force between these two here increases. Force between these two here increases means let the force between plus q and this charge is your F1, and since distance between plus q and this q here increases, so force between these two here decreases. F2 here in this direction. The net force is your F1 minus F2. It means that net force is acting in the direction of, in opposite direction of displacement. That net force is acting opposite direction of displacement. It means the particle, when it was at equilibrium position, it was in stable equilibrium. So when it is in stable equilibrium, then see important point here. So F net can be written as here F1 minus F2, and this further we can say 1 by 4 pi epsilon naught q by d by 2 minus x whole square minus of 1 by 4 pi epsilon naught q by d by 2 plus x whole square. Now when we are simplifying this, q by 4 pi epsilon naught, this will be your d by 2 plus x minus d by 2 minus x whole square by d square by 4 minus x square. Okay. Now further we are simplifying this. So what we will get, q cube by 4 pi epsilon naught. So this term become your 2 dx and by d square by 4 minus x square to the power square f net. See, interesting point here. So this is actually net force acting, and that net force acting in the left side direction. Now our displacement is very small, as x is very less as compared to d. Displacement very small. So if x is very small as compared to d, so here x term can be neglected or can be cancelled out. So what is left here? D square by 4 will left here, that we can write here now. So f net q into 2 dx by 4 pi epsilon naught d to the power 4 by 16. So this become 8q by pi epsilon naught d cube into x. This is your f net. Now in vector form if we are writing, so f net is acting opposite to direction of displacement. So we can write minus x like this. So acceleration, if m is the mass of a charged particle, so acceleration is here 8q by pi epsilon naught d cube into m and minus f. So this term is a constant and a is proportional to minus x. So this constant term called your omega square. The omega square will be your 8q by pi epsilon naught d cube into m. So t is equal to time period. So conclusion is that as a is proportional to minus x, so motion of the charged particle here, simple harmonic motion SHM. So what is the main point here? The positive charge is displaced slightly from mean position along the line joining the two charges. Then the equilibrium of the charged particle was stable, and if displacement of the charged particle is very small, then the charged particle will perform simple harmonic motion, and that can be given by this result, and time period of simple harmonic motion can be given by this relation. But this is not the only analysis of the question. See the analysis. Next, in the question it is not given which type of charge is there and in which direction we are displacing. Now this is the one part of the problem. Similarly, in the same question, if we are displacing charged particle perpendicular to line joining the two charges, see like this. Now in the previous section I discussed when the charged particle displays along the line joining the two charges, then the motion was your SHM and particle was performing simple harmonic motion. Now same question, but little bit difference is there. Difference is this: Now rather displacing charged particle along the line, if we are displacing charged particle perpendicular to this line, then what will happen? Then see the very interesting result. So now if we are displacing charged particle in perpendicular line here, suppose charged particle is slightly displaced by y distance, it is here. Now if we are talking about the forces on this charged particle, so one force is your let here due to this charge and another force due to this charge in this direction. So since charge q is displaced symmetrically about these two forces, these two charges, so forces are same in magnitude as well as in direction. So one component of force horizontal which cancel out and another component here vertically up. Now, so what we found here, resultant force on this charge is acting in this direction. Resultant force on this charge acting in this direction and our displacement is also in this direction, so that the equilibrium of this positive charge along the line normal to line joining two charges are your unstable equilibrium. As I said earlier, whenever resultant force acting on the charged particle and the direction of displacement are same, or resultant force is acting in the direction of displacement of charged particle on displaced position, then the particle will be in unstable equilibrium. So what will happen? As soon as after displacing, if charged particle is released here, then it will go in the direction of displacement. It will never come back to their mean position, or we can say their equilibrium position. So same charge, it was in a stable equilibrium along the line joining the two charges, but it is your unstable equilibrium perpendicular to line joining the two charges. This is a very, very important point. Now, second point. In this case, I took a positive charge. Suppose our charge is your negative. Same question. So this is just we are analyzing the situation. What is the effect of we are changing the charge, or what is the effect if we are displacing the point of displacing the charged particle in different direction. See, the very big difference comes. Now, suppose rather positive charge, if we are having negative charge and that negative charge kept between the two charges, then see the difference. Okay, first we will see along the line joining the two charges. So at the middle when the negative charge kept at the middle of these two, so okay, force of attraction by this in this side, force of attraction by this in this side. Since it is symmetrically placed and both charges are also same magnitude, so both forces will cancel, no problem at all. It means at this position particle is in equilibrium. At this position particle in equilibrium, but if we have to see the type of equilibrium, in type of equilibrium means now the charged particle is slightly displaced. If we are displacing charged particle by let x amount, so when charged particle reaches here, then what will happen? So the distance of charged particle from this charge will be your d by 2 minus x, and from this charge is your d by 2 plus x. So now when charged particle reaches here, since the distance of this charged particle from this charge decreases, the force of attraction F1 of this charge on this charge F1 will be more as compared to force of attraction of F on this, and which is acting in this direction. So what we found, since F1 is more than F2, so resultant force here act in the direction of F1, or resultant force is acting in the direction of displacement of charged particle. So whenever resultant force acting in the direction of displacement of charged particle, equilibrium of charged particle is your unstable. So what is the main conclusion here? When negative charge was there, then that negative charge was in unstable equilibrium along the line joining the two charges. But in the same question, if positive charge was there, that positive charge was in stable equilibrium along the line joining the two charges. Similarly, if the charge is displaced, perpendicular to line joining the two charges, suppose negative charge displaced here, and y is the displacement, then see the important point here. Displacement your upward. Since this is positive, this is negative, force of attraction, like this. Now if we will see the resultant force, component of the F in horizontal direction will cancel, only vertical direction will be there, and that vertical in downward. The resultant force will act in the downward direction, and that resultant force are in the opposite direction of displacement of the charged particle along this line. So what I found here, the force and displacement are in the opposite direction. So it means now the particle is in equilibrium, stable equilibrium along this line. So it is just the reverse case of the positive charge. Positive charge was in unstable equilibrium or along this line, but negative charge is in stable equilibrium along this line, and here positive charge was stable equilibrium along this line, and but negative charge your unstable equilibrium along this line. So as we are changing the charge, our equilibrium condition also changes, and line of equilibrium, if you are changing the displacement of line of displacement, then your equilibrium will also change. So this is the meaning of the analysis of the equilibrium of that point charge. So from here we concluded, okay, negative and positive charge also create a very big difference in the equilibrium position of the charged particle.